Yes, I'm here.
It's Lorian Knight.
And Daniel Page.
Yes, same as well.
Okay. Then we can start, I guess. Okay, welcome everybody to this session of actually the first scientific session for today with presentations. We have 6 presentations, so everybody gets totally 10 minutes presentation plus questions. The first presentation will be given by Annapurna Valivetti, and she will talk about second-order masked lookup table compression schemes. Please share your screen. And if you have questions, please use Zulip to ask your questions during the talk and after it.
Is my screen visible?
Yes, but not in presentation mode yet. Yes, now it's good.
Yeah. Hello everyone, I am Annapurna Valivetti, research scholar from IIIT Bangalore. I'll be presenting our work, second order mass lookup table compression scheme. It's a joint work with my advisor, Srinivas Vivek. So side channel attacks, no introduction, needs no introduction to this community. So there's a software the implementations of crypto algorithms are prone to side channel attacks. So masking is a popularly used countermeasure to counter side channel attacks. Along with security, the masking countermeasure can impact the timing and the memory requirements of the scheme. So the lower order masking schemes strike a balance between the memory and the memory and practical efficiency and the security. So the objective of our work is to balance the time, memory, and randomness for a second order masking scheme. On a high level, the side channel countermeasures to implement the nonlinear layer, the S-box of block cipher, is divided into two categories: the lookup table based and the circuit based schemes. Lookup table based schemes require more amount of memory. On the other hand, circuit based schemes require more online execution. So it's a good idea to balance the memory and the execution times, especially for in favor of resource constrained devices. So in this work, we'll be focusing on the optimizing the lookup table based schemes. So the idea of balancing the memory and time requirements is first discussed in the form of compression by Rao et al., which is a first order scheme. And later, this idea is extended to first and second orders by Vadnala. Even the memory required is also improved. So the high level idea of these compression schemes is to pack the table entries, the lookup table entries based on the higher order bits. More precisely, the lookup table will be divided into 2 subtables, T1 and T2. So the size of T1 and T2 will be decided by the compression parameter, and we'll have a set of shared random values across T1 and T2. But later, recently, Vivek demonstrated a second order attack on the second order scheme of Vadnala. So we aim to optimize the second order compression scheme, not only the security, but also the memory, randomness, and the online computation time. So the first, we came up with this idea of course, we initially randomized it to secure the tables from the attack of Vivek. We randomized the tables T1 and T2 using different output masks, but this is going to increase the randomness complexity of the scheme, which is going to be exponential in L. So we came with this idea of using a PRG, because ours is a second order scheme. We use a 3-wise independent PRG construction to optimize the randomness required. Further, we to improve the memory complexity of our scheme, we will not be storing the outputs of PRG. We'll be computing the outputs of PRG on the fly as and when required. And further, we slightly modified the construction of T1 to make it to pre-process, to make it offline. So pictorially, our scheme is divided into offline and online phases. As part of the offline phase, we will be generating the randomness required for the scheme. Further, we will construct T1. In the online phase, after the availability of the secret, we'll be constructing the second table T2 using the randoms and T1. And finally, we'll be outputting the shares of S of X. When it comes to the security of our scheme, we prove the security in the probing case model and composition. And the key observations I would like to highlight is, since the scheme is divided into offline and online constructions, is it possible to prove the security of T1 and T2? It is not, since we have a common randomness across T1 and T2. So the S-box itself is considered as a gadget. And the crux of the proof lies in showing the simulation when there is a shared set of random values used. We cannot simply use the one-time pad argument in this particular case. So this particular argument is a bit complex. So finally, I would like to conclude with our results. In particular, AES S-box require only 59 bytes instead of 256 bytes. It requires only 59 bytes of memory, which is a factor for reduction, and it requires only 19 bytes of randomness to protect the S-box second order S-box computation. And with pre-processing, if you would like to take the advantage of pre-processing, we'll be computing the tables for AES, all the 160 calls of S-box. We'll be pre-computing the tables, so which comes to 8.1 KB instead of on the other hand, the other table-based scheme requires 40 KB in this case. Even we implemented the lightweight cipher present to observe the improvements. It comes out to be 3.2 KB for present second order implementation. On the whole, our scheme strike a balance between the online execution time and the memory required, at the same time optimizing the randomness requirement. So this is a ePrint link for our work, and yeah, I'll be happy to answer questions if any.
Thank you. And we have one question from Benedict. Have you tested the practical security of your implementation? If not, will you make the code public?
Yeah, our code is public. We have in the ePrint link, we provide the link for the public repository of our code. We haven't tested the practical like on the using the tools. We provide the mathematical security proof.
Thank you. Thanks for making the code public, and thanks for answering the questions. Do you have any questions?
Yes, I was wondering, you say you need 59 bytes to store the S-box, the AES box. Does that include the T1 or tables or only the T2?
Including T1 and T2, along with randomness.
Nice.
Any more questions, anyone? I don't see any published anywhere yet. So if not, let's thank the speaker again. Thank you very much.
Thank you.
And we move on to the second presentation, which will be given by Pascal Cedric. Please share your screen. And it's about low latency hardware masking with application to AES. Okay, you can start. We see the slides perfectly. Okay.
Okay, thank you for the introduction, and welcome to the short talk on low latency hardware masking with application to AES. This was a joint work with Birgir Birgin, Michael Hutter, and Mark Marson while I was working at Rambus. Okay, so throughout this work, we tried to address the problem of low latency hardware masking. And as we already learned on Monday during the Ask Me Anything session with Ingrid, This is still an open problem and a challenge for hardware security. So for this work, we asked the following research question: can we actually implement masked hardware circuits that can be evaluated securely with low or ideally zero latency overhead? And as part of this overarching problem, we then addressed the challenges of finding a suitable hardware masking scheme, especially for low latency applications, and to eventually come up and build a secure round-based masked single cycle per round AES. So after some initial investigations and research, we decided to use the LUT-based masked dual rail precharge logic, in short LMDPL, which is a masking scheme that was initially presented at CHESS 2014. And this masking scheme actually describes a first-order secure gate-level masking technique to build and protect gadgets. And internally, each protected gadget is constructed of two layers, as you can see on the left figure, which is the operation layer and the mask table generation layer. In particular, the operation layer is constructed of monotonic gates and wiring only, and it's placed using some don't-touch constraints, but otherwise this masking scheme is actually technology independent. And in its initial proposal, it already comes with a 2-cycle latency due to its two-phase operation of precharge and evaluate that is actually independent of the protected function or the algorithm that is implemented using LMDPL. But as the original LMDPL paper from 2014 only argues about the security of the nonlinear gadgets using some non-standard activity image analysis, we first performed a theoretical security analysis of the LMDPL gadget to investigate the security of the gadgets under the more commonly used glitch extended probing security model. And as a matter of fact, we provide some security arguments in our paper that each nonlinear LMDPL gadget is first order secure, and it's first order glitch extended SNI actually. And gadgets can thus be composed freely and securely, even in glitching hardware circuits. However, these results only hold under the assumption that the operation layer circuit is implemented using some monotonic gates and wiring only, and each monotonic gate is precharged before operation, and the structure of the operation layer is kept intact during synthesis and place and route using some don't-touch constraints. Based on our theoretical security analysis, we had a closer look at the original LMDPL construction proposed at CHESS 2014. And for this architecture, the two-phase operation actually ensures the glitch-free operation and allows to build a 2-cycle per round AES design. However, we observed that if the operation layer is precharged and the table generation of all nonlinear gadgets is synchronized, we can actually freely compose all gadgets and build the entire AES round function as an LMDPL masked circuit. And then using the principle of duality, we duplicated the masked round function and could use one instance for evaluation while the second instance was actually precharged. And this operation was performed alternatingly then. So interestingly, we could use the same mask generation layer for both instances. So we didn't need to duplicate the mask layer. Since the mask generation did not require any precharging, but could be evaluated in a single cycle. So generalizing this approach, we can actually evaluate any M-round algorithm in M by N cycles just by constructing and duplicating an N-round evaluation circuit using LMDPL gadgets. And this enabled us to build a single cycle per round AES. So applying this approach to a round-based AES architecture, the nonlinear part, which is the S-box, can be built with a single cycle latency while only consuming 36 bits of fresh randomness per round. So comparing our results with alternative solutions in the literature, we can see that our proposal is quite competitive. And eventually, we constructed 6 different single cycle per round AES designs that allow any combination of encryption only, decryption only, or encryption-decryption with protected or standard key expansion. We then also synthesized those designs using the GF28 nanometer technology, and our encryption-only architecture, for instance, with protected key expansion, only takes up 157.5 kilogate equivalents, already including the PRNG that is needed to provide the fresh entropy for all S-boxes during every cycle. So using the encryption-only architecture with protected key expansion, we eventually also performed some practical security evaluations using TVLA for univariate and multivariate analysis. And we confirmed our theoretical security analysis because we could not observe any significant leakage in any of the observed statistical moments, even using up to 100 million power traces. However, for more details and some further security analysis, I also would like to refer to the recorded video and the paper. So in conclusion, we can state that LMDPL is a promising candidate for low latency masking, as it can be used to build first-order secure masked hardware circuits with zero latency overhead when we compare them to an unprotected design. Yeah, thank you for listening, and I'm happy to take any questions.
Thank you. There is no questions posted in the Zulip. I don't have an immediate question either. Yuval, do you?
I was wondering, yes, could this be extended to higher order masking?
So the initial LMDPL construction that we used was only proposed for first order security. So it is still an open question if we can build higher order LMDPL gadgets. I would be happy to see that we can actually build higher order LMDPL gadgets, but yeah, so far we didn't have an idea to build LMDPL for higher orders.
And there is another question coming up now on Zulip. What are the constraints on the design flow? Need to insert a coprocessor as a hard macro, for instance?
Yeah, as we said, the only constraints that we have is that we have to ensure that the operation layer of the gadgets are built using monotonic gates, and that this structure is kept intact using some don't touch constraints for the synthesizer and the design tools. But apart from that, we can just use any HDL code, and you can include this HDL code in your tool flow, so you don't need a hard macro for the entire design. We just have to ensure that those constraints, those synthesis and place and route constraints are kept for your tool flow.
And another question coming up, what is the size of an AES implementation in FPGA?
I don't have any numbers for that in mind. So since we just performed the synthesis and the evaluation for ASICs, I don't have any FPGA numbers.
You haven't implemented it FPGA, I guess.
No.
Another question is, do you believe glitch-free circuits are the most promising targets to apply hardware masking schemes without requiring an excessive amounts of registers?
Yeah, I think in general, the problem that we face when looking at hardware masking is glitches. And I think that's very well known. And yeah, one way to stop the glitches is inserting registers, but of course, this will increase the latency. So I think, I wouldn't say it's the most promising approach, but it is a promising approach. If we find other ways to stop the glitches, then of course we can avoid the registers, and this will be definitely better for low latency applications.
Okay, thank you very much. There is no more questions posted. Thank you.
Thank you.
For the presentation, and we move on to the next paper, which will be presented by Sigao, and it's about share slicing, friend or foe. Okay, we see your slides already. Just if you can put it in presentation mode. Yes. No.
Oh, sorry, I need to unmute myself first.
Yes, but also, okay, that's good.
Wait, so what?
You can start. We
Oh,
hear
yeah, yeah, okay.
you.
Sorry, thanks for the introduction. My name is Sigao, and I'm presenting a joint work with Ben, Dan, and Elizabeth. So we are at the final day of CHES already, so I guess everyone already familiar with the threat of side channel analysis. So one of the most prevalent countermeasure will be using masking. We already have a lot of off-the-shelf solutions. We have probably secure masking schemes in various secure models, and they often require the variables or the intermediate states satisfy certain security requirement. But on the other hand, we'll not only need the scheme, we also need a concrete implementation that's working in hardware or software platforms. In the hardware side, I would say the problem is relatively well understood. So take the threshold implementation, for example. We not only have the algorithm, the masking, well, the scheme, or even the implementation code, we also have specific instructions for engineers. For example, in the synthesize step, you have to have this option called keep hierarchy. So the synthesizer won't do something weird to your circuit. And also if something goes wrong, we know probably that's caused by this physical coupling effects. On the software side, I would rather say the situation is much more challenging. So first of all, we all know the scheme doesn't mean the same thing as your code. And even if you're coding in a higher language, high level language like C, that doesn't mean that's exactly the same thing as your code in assembly or binary, because that's the actual code running on your processor. Last but not least, we also have this opaque, big, huge commercial code lying behind, lying in front of us, which there's no way we can actually know what's actually running inside it. We know the logical formalization, but we can never know all the technical details. So considering all of that threat, we often talk about this auto reduction theory, which suggests if you store all the shares in different registers because of the unexpected leakage caused by transitions, whether by buses or registers, your security order in practice is often only a half of your security in your model. Our main topic in this talk will be the parallel masking in software. Well, previously, if you think about bit slice masking, one of the key issues there is trying to make the most of the provided bit width. So let's say if you have a 32-bit processor, what you're trying to do is always using concurrent blocks or other S boxes, trying to fill this 32-bit. Well, this might be challenging if you have a really short message encryption, or if you have some chaining mode, which is not really possible to predict the next encryption block. But in a few years ago, there's this new constructions that's dedicated to parallel implementation of masking. So in this scheme actually opened the opportunity of storing all the shares within one register, which in the end, of course, giving you much better efficiency, as you don't really need as many concurrent blocks or S boxes as before. Now you got much easier to get the best throughput you can possibly get. You got much easier ways to fit in the 32-bit processor. But remember here, I only say, well, from now on in the following part of the talk, I will call this share slicing. But remember here, I only says possibly, because the original proposal never really said, they only proposed the security model and security assumption. They never really said this fit for software implementation or hardware implementation or whatever platform you're using. So the next question we are going to discuss is whether this is actually a good implementation on the software platform. So if we look at the hardware side and consider the security assumption here we assume each part of the share is leaking independently. There are no like crosstalk or interaction with each other. In the hardware set, if we look at the threshold implementation, this is much more, well, I would say better supported. If you look at this graph, each of the blue circles by design, they are computed as an independent unit. Until the next stage, they won't really interact or communicate with each other. This is part of the feature we inherit from the MPC. But if this kind of form some architecture support for this independent assumption. But if you take that to your software side and storing all the shares within one register, that basically means if you want the same kind of scrutiny, then each gate in your processor must connect to or link to only one bit within the bit width, which is quite unlikely to be true, to be honest. If we consider one example like the barrel shifter, because it can perform arbitrary shifting results, then each output bit is almost have to connect to all of the input bits, which is already a contradiction to this assumption. And also, if you consider the adder, which have a huge carry chain, which can also be an contradiction to this assumption. So it turns out you can actually explore the such leakage. We only present the first order thing here. So if you are using 4 shares masquerade AES, the surprising result might be you can actually still spot first order leakage here, which is already a contradiction to the order reduction theory. And it can actually affect your security in practice, maybe not to a huge amount, but yeah, it actually affects your security in practice. So our take-home message would be like I think it's fair to say the independent assumption shouldn't really be taken for granted. If you take a look at the software side of the story, and unlike its counterpart on the hardware side, there are no architecture support anyway. But I will also like to claim like our paper or our result doesn't really suggest share slicing should be forbidden. Maybe you can switch for a slightly weaker assumption. Let's say I know there are interaction, but the interaction on the software side, on the software processor, the processor I'm using is not really that strong. So I can perhaps ignore it for a while. Or the other thing I would like to mention is we did not claim shifter is the only source or the correct source of the interaction we observe here. So as I already said, there are various components like the adder might be able to contribute here. So perhaps the most important question here is, what does our model assumption means in practice? So if we think about the academic world, we always offer masking schemes in certain security models, but in the industry side, the engineer actually needs some connections. What does our model assumption means? In what kind of platform our model assumption is absolutely true, where it can be maybe not true, and where they have to pay attention to. So who would be the interpreter standing in the middle, converting all the wisdom, all the results, and all the precautions happening in academic research to the industry without losing important bits and preconditions or assumptions? That's probably a question to ask or as a community. And that concludes my talk. If you have any questions, I'll be happy to answer it.
Thank you very much. I don't see questions in Zulip. You have done this for ARM processors, right?
Yeah, M0 and M3.
Yeah. Have you worked with RISC-V?
Oh, no, we haven't. Yeah, that's part of the plan in the future, but we haven't really tried this with RISC-V. So yeah, I guess
there's much more control, and you can see. I mean,
yeah, you can actually see often. Yeah, but I'm not so sure. So if you ask for the same sort of scrutiny as threshold implementation, then I guess the shifter will always be a problem, and also the adder. But if you're saying we don't want the same level of scrutiny, I said you can connect to several different shares, but I said the leakage is not that strong, then that's another type of argument, I would say.
But couldn't you see that easier where the leakage comes from and trace?
Yeah, we can definitely see the leakage coming from, where the leakage is coming from. I think probably the shifter and adder will still contribute to that.
There's one question coming up. There has been suggestions for doing something analogous to share slicing using vector units, like neon, instead of plain bitwise arithmetic. What do you think of such approaches?
Well, I think that depends on how ARM is designing that type of core. If it's like a separate logic circuit that only connect each bit with each, well, let's say there are no like adder or shifter or any conventional circuit that mix all the bits together, then I guess that should be fine. Of course, it's probably worthwhile to still test it, but if that's the case, that should be fine. If we, in like open source designs like RISC-V, we did coprocessors that's actually working with all the assumptions and keeping that in mind when you're designing it, then that's probably also fine. But we don't really know for ARM. And I don't really know whether they will be willing to publish their design or not. Probably not, but yeah.
Okay, Yuval?
No questions from my side.
Okay, thank you very much. And we can move on to the next speaker. Yuval, you take over?
Yep, thank you. And the next speaker is Licha Wu, and will present, Licha will present remove some noise on pre-processing of side channel measurements with autoencoders. Licha, the stage is yours.
Can you see a slide?
Yes, we see
Yes.
the slide.
Perfect. Thanks for the introduction, and welcome to this presentation. The topic of this presentation is remove some noise on preprocessing of side channel measurements with autoencoders. The authors are Licha Wu and Stefan Pisek from TU Delft. So as we all know, the side channel analysis has been proved to be successful in both hardware and software. And the developer will notice that, and they develop several countermeasures to increase the security level of the product. And for us, for the attacker, it makes our life difficult because these countermeasures, together with the noise, reduce the correlation between the traces and the real data being processed, and the side channel analysis become more difficult to perform. So as an attacker, the goal is to remove the noise. For the single type of noise, it's possible. For example, we can use averaging to remove the Gaussian noise, use a static alignment to remove the misalignment. But consider a more realistic scenario that you have the combination of noise and countermeasures in the traces. Up to now, there's no universal way to do that, and this is a motivation for us. And our proposal is that we want to use the denoising autoencoder to do that. The goal of an denoising autoencoder is to map the relationship between the input noisy traces and output clean traces. And a well-trained denoising autoencoder can keep the most important features in its latent space, which is in the middle of this graph. And then we can feed the new but unseen noisy traces to the trained denoising autoencoders. And ideally, the clean traces can be reconstructed. So to validate the usage of the denoising autoencoders, we designed two different denoising strategies for both white box settings, which is for the evaluation scheme, and for the black box settings, which is for the attackers. And due to the time limit, we only show two different type of noise and countermeasures. The first is desynchronization, and then there's combined noise. And for the rest of them, you can find it in the paper. First, we will introduce the denoising strategies for the white box settings. So similar for the profiling attack, we'll assume the attacker have the full control of the device. We call it device A. And with this device A, an attacker can retrieve two different types of decay traces. One is with a countermeasure on, and one is with a countermeasure off. So one is the clean traces, one is noisy traces. And with this noisy clean traces pair, he can train the denoising autoencoders. And then he can use the noisy traces from the device B, which is a device under attack, feed it into the denoising autoencoders. And ideally, the clean traces can be reconstructed and the attack performance will be increased. To validate that, first we will demonstrate here the denoising performance of the desynchronization. So the desynchronization is really common in the side channel traces, and we attack them with a different attack method. And as can be seen here, with the best attack result, the gas entropy do not reach 0, which means that the correct key cannot be retrieved within 10,000 traces. However, with the denoising autoencoders, the denoising performance is dramatically improved. And also note that we benchmark our denoising autoencoders performance with a static alignment, which is a normal alignment method. And as can be seen here, the performance of the denoising autoencoder is actually better than static alignment, which proves that the denoising autoencoder have efficiency in remove a single type of noise. And then we go to a more extreme cases. We add all of the countermeasures and noise into the traces, which makes the traces super noisy. And as expected, with the best attack method, the key cannot be retrieved, and we do not even see the Gaussian entropy is converging. However, with the denoising autoencoder, you can clearly see on the right graph, you can clearly see that the Gaussian entropy is converging to 30 with 10,000 traces. And as a benchmark for the frequency analysis, the Gaussian entropy is just flat, meaning that the built PDF do not learn anything. After the white box settings, we go to the black box settings. Note that the difference between the white box settings and the black box setting is that for the black box settings, an attacker do not have control of the device. In other words, the clean traces is not that easy to acquire. We will notice these limitations and we investigate our usage of the denoising autoencoders. But luckily, we found that there are certain tolerance of the denoising autoencoders in terms of noise. So here, instead of training the denoising autoencoder with the noisy clean traces pair, we train this with the noisy less noisy traces pair. So here, we assume that an attacker have certain ways to remove the effect of noise with special method and acquire a small amount of the less noisy traces. And he train the denoising autoencoder with noisy less noisy traces pairs, and the features can be learned in the latent space. Here we also demonstrate our strategies for the Gaussian noise and desynchronizations. And here note that for the less noisy traces, for the Gaussian noise, it's acquired from the averaging. For the desynchronization, it's acquired from the static alignment. And compared with, for the attack result, compared with the noisy version, the attack performance is dramatically improved. Finally, we move to the conclusion and the future works. In this paper, we demonstrate that the denoising autoencoder can remove and reduce various types of noise, countermeasures, and their combinations. Our approach is especially powerful for the white box settings, but we also demonstrate the potential in the black box settings. For the future work, we want to use a denoising autoencoder to deal with the portability problem, because it's kind of a noise-like problem. And also, we want to use the encoder of the denoising autoencoder to launch attack. Thanks for your attention.
Thank you, Licha, for the presentation. We have a couple of questions in the Zulip channel. First question is from Marius Omar Chudari, and the question is, on white box settings with combined measures, after applying your autoencoder technique, why template attacks do not work at all in decreasing Gaussian entropy?
I think that's a reason because the denoising autoencoder cannot perfectly remove all of the noise. So we expected that the noise, the effect of the noise will be reduced, but there still have the noise. And compared with the deep learning attack, probably the tolerance, for the template attack, the tolerance of the noise is not that good. So there are some countermeasures that template attack cannot deal with.
Thank you. And Guillaume Barbou asks, thanks for the talk. Do you use some kind of upsampling as part of the deconvolution blocks of the decoder?
Yes, we do.
And also, did you consider attacking the encoder output?
Attacking the encoder output. Well, that is for the future work. As we said here, we can use the output of the encoder because the feature is learned in the output of the encoder. So we expected that we can use the encoder to attack.
Thank you. And Leonard Wouters asks, could you provide us with an intuition for when to use the adding some noise technique and when to use the removing some noise technique in the black box setting?
So for the adding some noise, it's always a good method because it provides a regulation factors, and according to the previous research, it will increase the attack performance. But note that the adding some noise paper, there's a certain threshold, so there's a limitation of adding noise. If you add too much noise, then the adding some noise will not work. So if you have too much noise and you see that for the attack performance, the Gaussian entropy is not converging, so please use our remove some noise method.
Okay, thank you very much.
Thank you.
And no more questions. It's time for the next talk. And the next talk is presented by Florian Unterstein. And the title is Retrofitting Leakage Resilient Authenticated Encryption to Microcontrollers. Florian.
Okay, thank you and good morning to everyone. So the main
we only see half your screen.
Oh, okay.
Stop sharing and try again.
So but you see the slides, right?
Yes.
We see the part of it, yes.
Okay.
Close
Maybe
the
I try sharing the entire screen.
Yep.
And then
Still half.
okay. Okay. So you still see only half the screen?
Yes.
Yes.
Okay, I only have one screen, so I don't know what's going on. Maybe.
Do you have
part of the Zoom app is probably on the right half of your screen covering that. If you can close any chat or any other piece of the Zoom app or make it small.
Yeah, I'm in the browser, so all I have open is the PDF. So
and the browser is open?
Yeah, the browser is open.
We're seeing the left half of your screen, so maybe you have to kind of make your PDF
Yeah,
smaller and then move it on the left half of the screen.
This problem is nearly impossible to solve, as I remember. Other people have encountered this problem. I think what you need to do is send your slides to someone else.
Well, if you can do it like this.
Oh, yeah,
I think, yeah.
Yes.
Okay, that's okay. Bit smaller, bit smaller.
Getting there.
Bit smaller again.
Like this?
A little bit more. So yeah.
Yeah,
that's
that's
it.
okay.
Yeah.
That's fine.
Excellent.
Okay, perfect start. Again, I have to do the manual scrolling, but that's okay.
Yeah.
Good. So welcome again. I hope the rest goes smoother. So the main question we wanted to answer in our paper was how to retrofit side channel protection to microcontrollers. And we started with two simple observations. So the first is the software countermeasures like masking can be too costly to implement. And as we have heard in the other talk, it is also not that easy to get it right. And then second, many microcontrollers already have hardware crypto accelerators, but unfortunately, they almost never come with any form of side channel protection. So our main contribution is that we show how to use those unprotected hardware accelerators to secure authenticated encryption using concepts from leakage resilience. So here you can see the leakage resilient authenticated encryption scheme that we are using. It was proposed by Gabriele et al. At AsiaCrypt. And it basically consists of three building blocks. So we have a leakage resilient pseudorandom function, a leakage resilient pseudorandom generator, and a hash function. In our case, we're using SHA-256. And the PRF is used twice in the scheme. So in general, it is divided into an encryption part and a MAC part. So the upper part here is the encryption. And we use the PRF and the encryption key to process the nonce into a seed for the PRG. And the PRG then outputs the key stream that we use to encrypt the message. For the MAC part, we first process all the inputs, so the message, the nonce, associated data with the hash function to get a fixed length input to the PRF. And then we use KMAC to process it and get the tag. Now, what is interesting about this scheme is that the long-term keys, the encryption key and the MAC key, are only processed by the PRF. And what this means is that if you want to secure this against side channel attacks, all we need to do is secure this PRF building block against side channel attacks. So what does this mean for our microcontrollers? So if we can implement a secure leakage resilient pseudorandom function on our microcontroller, then we can implement the scheme because the rest of the scheme it's not security critical. We can just do it in software or use existing other hardware accelerators if we have them, for example, for the hash function. So how do we build such a PRF? Fortunately, we can do it using just a single AES core as building block. So on the right, you can see the data flow graph of such a PRF. I won't go into details now, but the most important fact is that the only hardware block that we need is a standard AES core, and all the rest, so the side channel security, is based on how we use that core. And the two key ideas that we are using is limited data complexity, so the number of inputs under one key is limited. And inside the AES, we make use of parallel hardware, so parallel S boxes, to generate algorithmic noise. So, like I said, the only hardware requirement that we have is this AES with parallel S boxes. But luckily for us, this is a feature that common microcontrollers often have, because if they have a crypto accelerator, then it is used to enhance the performance, and this is mostly done by either fully parallel implementations or at least 4 S boxes in parallel to speed up the computation. So now coming to our proposed construction. This means that we can port this PRF to microcontrollers. So what we do is we use the existing AES to do all the encryptions that are happening inside the PRF. And then we do all the rest, the protocol handling, the key updates, the generation of the inputs in the software on the CPU. And then if we can show that this can be implemented securely on our microcontroller, then we can also implement the full AAD scheme. But this is the one task that is still to do. So we need to show that actually we can use it and it's not leaking excessively. So for this, we identify 2 attack vectors. The first one is, of course, the AES itself. So when we use it in the limited data complexity setting that we have through the PRF, then it should not leak too much. And the second attack vector is the bus transfer of the key and the ciphertext, because this will be the key for the next iteration. And since this is not a security controller, but just a common microcontroller, the bus is of course not encrypted. So the key goes over the bus in plain. And therefore we also need to consider this attack vector. So in the paper, you can find a side channel analysis of the PRF with different configurations for the data complexity, because this has an impact on the security and the performance for 2 microcontrollers that we use. The main difference between the 2 is that they have different number of parallel S boxes. So both are ARM Cortex controllers, but the one has an accelerator with 16 S boxes, so fully parallel, and the other one with 4 S boxes. And this makes a difference in the security that we achieve. So I have to skip over the results in this short talk and we'll go straight to the conclusion. So what we find is that for both controllers, we can find implementations that achieve a security level of over 100 bits. So our construction therefore provides resilience against side channel attacks in this setting. And we also perform a performance analysis and a memory overhead analysis and find that the impact is quite small and reasonable. And in my opinion, most importantly, it's applicable to a wide range of microcontrollers. So all that we need is just an AES with parallel hardware, and then we can implement this scheme. And we also open sourced the source code, and you can find it under this link. So thanks for dealing with the technical issues and listening to my talk.
Thank you very much for the presentation. We have time for a short question. I don't any, but I have a question. What is the performance of the scheme?
So the biggest impact on the performance is, of course, the PRF, because depending on the configuration, it takes up to 129 AES cores. But it only needs to be executed twice. And then the main payload, so every block that we want to encrypt, takes 2 AES cores. So we have the full figures and numbers in the paper, but as a rough estimate, you need those, let's say, 256 AES cores in the worst case for the initialization, and then for every block of data, 2 AES cores. You can find the exact cycle counts for different configurations and inputs in the paper.
Cool. Thank you very much. I don't see other questions. So we will move to the next talk. And the next talk is presented by Dan Page, and the title is Fennel and ISE to mitigate analog microarchitectural leakage. Dan?
Okay, can you see the slides okay?
Yes.
Yes, thank you.
Okay, great. Yeah, so this is joint work with C, Gao, Ben Marshall, and Thin Pham. This is to do with an ISE that concerns the improvements of security characteristics of software implementations of cryptography, rather than sort of performance characteristics in some way. So I want to start really by talking about the problem initially. This is a kind of standard diagram that you might show someone, a textbook style diagram of the layers of abstraction in a typical computer system. The interesting part from our perspective is the middle, which is the instruction set architecture, or ISA. This acts as a kind of an interface or a contract between hardware and software, in the sense that the ISA defines a set of architectural resources and instruction semantics, but it doesn't define how those instruction semantics are realized in practice. The underlying hardware, the microarchitecture, is free to make a choice in that respect and optimize towards whatever goals make sense. So this description of an interface is kind of important in traditional computer architecture, I would say. And so people write papers about the importance of this. The one that's cited on the slide here by Dunham and Beard really makes the argument that this interface should be adhered to strictly so that we get these advantages of flexibility in the underlying hardware. In reality, of course, if you look at concrete ISAs, the interface is already somewhat transparent. So features in the ISA such as memory access and branch delay slots and so-called fence or barrier instructions kind of go between the two worlds. So in some sense, they expose some of the microarchitectural detail to the software that's being executed on it already. So bearing that in mind, you might wonder, well, why not take things one step further? And indeed, that's what Guy, Jerome, and Heiser did with their proposal for the AISA, or augmented ISA. So their argument is that in certain scenarios, it makes sense and maybe is actually vital to expose details of the microarchitecture to the software that runs on it. And their argument is motivated by security, essentially. For certain classes of attack, particularly those involving the microarchitecture in some way, you need to have knowledge of the microarchitecture and to some degree control over it if you're going to construct robust countermeasures. So essentially what we've done is examine an instance of this type of concept within the context of analog microarchitectural leakage. So that's leakage that stems from the use of for capturing power analysis or EM style analysis. I think the easiest way to describe what Fennel is doing is by analogy, actually. So if you consider a sequence of instructions, the idea is that in general, it's possible to sort of separate this sequence into two parts, a left-hand part, so a green section, and a right-hand part, a blue section, using a fence instruction in the middle. And the idea is that this fence instruction controls interaction between the green part and the blue part in some way. The most obvious example of these fence or barrier instructions is to do with memory access. So almost every ISA includes some form of fence that allows you to control how memory is accessed and ensure consistency in some way, shape, or form. What Fennel does is use a similar type of concept, but applies it to leakage. So basically, Fennel is a fence instruction for leakage in the sense that it's meant to control interaction between the green part and the blue part of your instruction stream in terms of the leakage characteristics of those instructions. Concretely, what that means is that Fennel introduces a configurable fence instruction that resets or flushes microarchitectural resources as it progresses through stages of execution. So for example, this prevents later instructions in the blue parts overwriting microarchitectural content or values that were placed there by the green parts. We implemented Fennel on 2 different RISC-V compliant microarchitectures, one of our own design and one the Pico RV32. This slide is meant to just capture a simple example to illustrate what's going on. So this is an ISW multiplication kernel, which you might see as within a sort of masked software implementation. The idea on the right-hand side is if you look at a TVLA-based leakage assessment, this leaks fairly strongly, but we're able to control that leakage by placing fence instructions selectively within the kernel and configuring them appropriately. So eventually we almost eliminate the leakage that we had in the first place. So I think the thing I'd like to concentrate on is the concept here rather than necessarily our implementation, although clearly there's a lot more details of that implementation in the paper and the longer video. The key thing basically is that Fennel as a concept allows us to give stronger guarantees about what goes on in the underlying microarchitecture by selectively exposing components of it to software. This is important insofar as, of course, that software and the algorithms and theory around it will, you know, any proofs about that will be based on that sort of assumption. So we're able to use Fennel to localize leakage, so find out where it is. We're able to use Fennel to reduce leakage or control it in some way, and as some form of practical anchor for theoretical reasoning about leakage. This session is called SCA Countermeasures. I wouldn't view this as a countermeasure per se, but simply as a way of improving the quality of existing countermeasures in some way. Okay, so that's it. Happy to answer any questions.
Thank you, Dan, for the talk. We have a question. Can you say a few words about overhead, e.g. for software AES?
Yeah, so the numbers for this are in the paper, so maybe I have to defer to that to give an exact answer, but there's sort of 2 features here. One is an obvious feature that you have to place these additional instructions, these fences, so those impose some overheads just naturally. But there's also a more subtle overhead, and that's to do with the forwarding logic in any pipeline's microarchitecture. So this forwarding logic sort of inherently breaks the idea of isolating the left hand and the right hand, the green and the blue parts of our instruction stream. And so in order to cope with this and make sure that they're isolated in terms of leakage, you pay an additional penalty or overhead. And of course, that depends on the instruction stream itself, what that actually is in practice, but it can be relatively significant.
Thank you. Chester asks, what do you predict about the runtime overhead on larger or out-of-order processors?
Yeah, so this is a good question. There's a range of different next questions, what we would do next, feature work. And the most obvious of that is exactly, how do we apply this sort of idea to more complex microarchitectures like out-of-order designs? I think the answer to that is a difficult one. I don't really have a precise answer. I mean, as soon as you look at out-of-order designs, there's so much going on at the same time, then managing that using a system like this is much more difficult than the sorts of in-order pipelines that we've looked at so far, at least. So I think the honest answer is, yeah, we don't necessarily know what the answer there is, but it's certainly an interesting question and one we'd like to follow up.
Yes, well, I guess you could always flush the pipe.
You could force it into an in-order. One idea we had is that you force the pipeline into an in-order mode when you're executing security critical stuff. So you have sort of at least some more control because, yeah, I think limiting the complexity in some ways is going to be necessary.
Mm-hmm. Svetla, any more questions? Okay, thank you very much for that. This concludes our session. So many thanks to all the speakers and to all the authors and the audience. It's been a pleasure. And I think we move to the social app from now.
Thank you very much, everybody.